Hi guys, this is the second instalment of our C1 video. So this is part 2 for the video you've already watched. Today we're going to be looking at the history of the atom and how that's changed over time. We're also going to look at the difference between ions, isotopes and atoms. And the third thing we're going to look at is electron structure. So this is everything you're going to find in your Caboodle login, and it's just going into a small amount of detail to help your understanding. Okay, so this is a timeline to show how the atom, or our understanding of the atom, has changed over time. So initially, when we first got an idea about this, I think it was the ancient Greeks, but the first person to put forward any research on this was Dalton. So he decided that all of these elements were slightly different in their mass, which means how much material they're made up of. So in the next part, we're going to look at what that material would be. So through his research, he decided that these balls were small and indivisible. So although he was not correct with that, he was correct in the idea that all of these atoms of elements recombine during a chemical reaction and come back in a different arrangement. The next significant piece of research came from Thomson. He found evidence for the existence of the electron. He used beams of particles that were attracted to positive charge. This suggested that the particles themselves were negatively charged. This finding brought about the plum pudding model. He suggested that the negative charge of the electrons were embedded in a cloud of positive charge. This therefore refuted Dalton's idea that atoms were indivisible. The model changed again when the researchers Geiger and Marsden found evidence for the existence of the nucleus. Their research was named the gold foil experiment after they fired positively charged particles at a thin sheet of foil. Their findings were interesting because although some of the positively charged particles passed all the way through, some deflected directly back towards them. This told them that the positive charge was concentrated in the centre rather than spread out in a cloud like suggested by Thomson. Bohr's findings caused for a change in the model once again. Bohr's research is actually really interesting because it's the same explanation that we use to explain why we see the northern lights. He suggested that electrons were found in energy shells. So you can see in his diagram the electrons have been separated different distances away from the nucleus. Bohr found this from heating different atoms and seeing that the light given out had different amounts of energy. He concluded that the light given out was caused by an electron falling from a higher energy level to a lower energy level. The final model that we are interested in was put forward by Chadwick. This is probably the most common model that you will have seen used in a science classroom. Scientists had noticed that there is a difference in mass other than just the protons. We already had evidence from the protons thanks to the research by Geiger and Marsden. However, we had no evidence for our neutrons that we find inside the nucleus. Due to neutrons having no charge, it's difficult to identify their presence. Here is the model of Chadwick's experiment. You do not need to know this in detail. All you need to know is that Chadwick's research found the evidence for the neutrons inside the nucleus. All of the research that you've heard about has combined to make this final model. Although it's not a perfectly accurate model, it does enable us to discuss what happens to an atom during a chemical reaction. Here are some key bits that you need to know. The atom is made up of protons, neutrons and electrons. We talk about mass in a relative term. This is because it's not heavy enough to be measured in things such as grams, therefore we compare them to one another. This means that protons and neutrons have the same mass. An electron is 2,000 times lighter than a neutron or a proton. As well as this, we know the charge of these subatomic particles. A proton is positive, a neutron is neutral, and an electron is negative. This means that the positive charge comes from within the nucleus, and the negative charge comes from the electrons in the outside orbiting the nucleus. Now, if we want to know how many protons, neutrons, and electrons an atom is made up of, we need to talk about the atomic number and the mass number. The atomic number is the one that you'll find in the top left-hand corner. This tells us how many protons an atom has. The bottom number and the larger number is the mass number. I always remember this, that mass is massive. It's the largest one of the two. So the mass number is how many protons plus neutrons you have. So in the example of carbon, the mass number is telling us that we have 12 protons plus neutrons. And the atomic number is telling us that of that 12, 6 are protons. So obviously 6 are going to be neutrons. Although we don't have something indicating how many electrons we have, it's really easy to work it out. An atom is overall neutral. This means it has equal positive charge and equal negative charge. If you remember from our previous slide, the protons provide the positive charge and the electrons provide the negative charge. Therefore, if we have 6 protons, we must also have 6 electrons within our atom. Here is a breakdown of what carbon is made up of. Using the information, see if you can work out what fluorine is made up of. Remembering that the atomic number tells us how many protons, the mass number tells us how many protons plus neutrons, and the electrons are equal to the protons because an atom is overall neutral. Also, just to note on this one that your periodic table would round the 18 to 19. I'm about to unveil the answer, so if you're not ready, pause the video. Yep, I was a little bit sneaky here, and I picked one that didn't have equal number of protons and neutrons. So although that's normally the case, I wanted to make the point that sometimes the protons are not equal to the neutrons. I hope I didn't trip too many of you up, so we should have 9 protons, 10 neutrons and 9 electrons. So now we're going to move on to looking at how these electrons would be arranged. So I've called this electron configuration, but you may also hear it referred to as electron arrangement. They both mean the same thing. It's pretty much just looking at the pattern of electrons orbiting a nucleus. So I've made this diagram that looks at the first few atoms and how their electrons are arranged. With this video, I'm going to attach a worksheet because I think there's real merit in drawing out the electron configurations yourself. It helps you to see the patterns across a period and down a group. Hopefully you can see here that as we go across the period, the atomic number increases. This is because the periodic table is arranged in increasing atomic number. So we go from hydrogen with 1 electron to helium with 2. When we move on to lithium, something interesting happens. When we start the next period, we get another electron shell. This shows that the next electron is in a higher energy level. However, it's also important for us because it shows us that the first electron shell can only hold 2 electrons. The rule you need to remember for this is that 2882. The first electron shell can hold 2 electrons, the second electron shell can hold 8, the third electron shell can also hold 8, and the fourth electron shell can only hold 2. So electrons must fill the lowest energy level before they start occupying a higher energy level. So it's almost like you guys in assembly. You would always fill up the first row before you move to start a new row. Hopefully you can see that as we move across period 2. As a new electron comes, it fills in next to the old because that electron shell is not yet complete. So although it might not seem like it now, electron configuration is really important. It underpins loads of things that we're going to do in the future, such as forming ions, writing formulae, and even predicting how elements will react. Okay, sorry, but this video has ended up being a little bit longer than I'd hoped, but this is the very last thing we need to look at. We're going to compare the differences between atoms, ions, and isotopes. So an atom is likely to be the most common one we'll talk about. It's almost like the most basic version. What I mean by that is that it's not changed in any way, unlike the other two. So the next one is an ion. This is a charged particle. So this occurs when an atom loses or gains an outer electron. So what that means is we can take on electrons from other atoms or we can give electrons to other atoms. So we'll look at that when we come on to bonding. But because electrons have a negative charge, if an atom gains an electron, it becomes a negative ion. If an atom loses an electron, it becomes a positive ion. This is because we've caused an imbalance between the protons and the electrons. And finally, we have isotopes. So these are versions of the same elements but with more or less neutrons. This means that the isotopes will have the same chemical properties because they still interact in the same way due to having the same number of electrons. However, they might have different physical properties. So for example, if they've got more neutrons, they will have a higher density because there's more mass within the atom. One negative of isotopes is that often due to the excess of neutrons within the nucleus, they become radioactive because their nucleus is unstable. Because most isotopes are naturally occurring, this is where we get their mass number from. It's an average of the isotopes that are naturally occurring within our environment. So chlorine is a nice example because chlorine has a decimal point within its atomic mass. The mass of chlorine is 35.5. This suggests that we have 50% isotopes of chlorine 35 and 50% isotopes of chlorine 36. So that was a skim over of the second part of C1. Again, apologies that it ran over, but I hope you found it useful.